Okay, so I didn't realize that apparently my camera shuts itself off after recording for a certain amount of time. So, yeah, I don't know when that stopped recording, but so I'll try and recap briefly. I like this problem because it has there's a lot of interesting things that happen with it, particularly with respect to the differential equation method. This problem is this is half of your pre-lab, half of one half of your pre-lab. Yes, so well, let's get started. Let's try and figure out what to do. First thing is always draw your moment diagram. This is a cantilever. We have a non-zero moment here. So if I draw my moment diagram, it's going to look something like this. This is going to be PKL, and this is going to be KL. This is going to be 1 minus K times L. Sorry, this should be negative P. PKL, yes. So where do we begin? Let's write an equation for this. The equation for my moment diagram, my m of x is going to be equal to negative pkl plus px. And this is from, it's going to be a piecewise function. This is x less than kl, so x greater than kl. Okay. Now, when I'm using my differential equation method, you normally go from theta. Okay, so I'm going to say right now that I usually draw out my EIs and add them in at the very end, because I find EIs to be very tedious to carry through differential equations, because either you add it onto every term or you have an extra set of parentheses, and you have enough parentheses that it's too much of a hassle. So I normally draw my EIs. It's a bad habit, but it's a convenient one, I find. Anyway, you normally integrate from 0. Your theta is normally your integral of m of x. But this only applies for continuous moment equations. Notice how our moment, or I should not, it's not continuous. This only applies for smooth moment equations. Notice that our moment diagram here is not smooth. We have two equations to express this moment diagram because we have two lines. We have a linear portion here and a constant portion here. So when I integrate this, I need to split this up into two integrals. But there's a lot of tricky stuff that ends up happening. So what I'm going to do is I'm going to just say, well, let's just integrate from 0 to KL first. I want to find the deflection and rotation at C, but let's find the rotation and deflection at the point where my moment diagram ends first. And I should say that I'm going to solve this using several different methods. I'm going to solve this using, or not several, I'm going to solve this using differential equation method first, and then with moment area second. Because someone in office hours today was doing this problem, and I realized that differential equations for this particular method ends up being a very, very interesting solution. So yes, we have our moment equation. I have a moment equation here. So if I do this, this is negative pklx plus px squared on 2 from 0 to kl. This is kl. Theta at kl plus a. If I say check, this is going to go to 0. This is my constant of integration. I need to include it when I'm doing differential equation method. But in our case, if I plug in theta of 0, when x is 0, or theta of 0 equals 0, right? Because I'm in a cantilever. When I plug in x equals 0 and x equals 0, all these terms go away. I'm just left with a. So a is 0. So my theta KL is going to be PKL square over 2. And this is going to be negative p KL squared over 2EI. Okay, so we have this. Now, in order to find deflection, we need to integrate. Note that I plugged everything in already. For deflection, you cannot use this equation. You have to use your original theta of x equation. And you might be like, well, shouldn't that give you the same answer? And it actually does not. You have to plug in your limits of integration at the very end. That has to be the very last step. You cannot plug in beforehand. And if you do plug it in beforehand, you'll see what's happening here. Your coefficients here will change. If I just integrate this step, I will not have the 1/3 term that appears. So let's see what I mean. This is going to be equal to negative pklx squared. I hope I'm not confusing anyone else by mentioning this, but notice that if I just integrate this statement, I will not get this statement. So something to keep in mind. When I do this, my delta KL equals this. When I plug everything in, I'm not going to show you the intermediate steps, but delta at KL is going to be equal to negative P KL cubed over 3EI. Okay, so you're like, okay, this is all good, but I want to find the deflection and rotation at the end. I don't care about what's going on in the middle. Well, it turns out that you need this for the next step. Remember where I said that your moment diagram was not smooth and you need to split it up into two? Well, you're going to integrate the second step now. And like, well, so I'm going to start this from x prime. I did x from here to here, and I'm going to do x prime from here to here. So I'm going to say do 1 minus k L times m of x. And I'm like, well, notice that the m of x here is just 0. So my integral is actually going to be the integral of 0. You might say, well, this is pointless. Why would I do this? And it turns out you have to do this because you pick up a constant of integration equals c. And now if I plug in theta of 0 equals c equals theta at KL. What I'm saying here is that I did one equation from here to here, and now I'm doing one equation from here to here. So this is my new 0. So the 0 in this equation is actually the KL, the KL in my first equation. So the value I found here, I'm going to bring this down into here. And I have a feeling this is going to cause a lot of confusion, but it should end up making sense when I do it another way later on. So just follow through for now. Beta KL. And this, notice what the implication of this is. My theta of x equals c equals negative pkl squared over 2ei. My theta, there's no x term in here. This means my theta is constant from p to the end, and that is what you should expect because your moment is 0. If you have no moment here, you have no change in rotation. So my theta at c, at point C, is going to be equal to negative pk all squared over 2EI. Now let's look at deflection. Yes, I picked up, I reintroduced my EIs here. Notice how I reintroduced my EIs. I haven't mentioned this because I just do this by second nature, but I reintroduced my EIs after I'm done with all my integration and plugging in. My delta of x is going to be equal to 0 to 1 minus KL theta of x. That is equal to C of x plus D, from 0 to 1 minus K times L. So then what happens? What is D? When I say delta of 0 equals D, like when I plug in x equals 0, the only thing that's left is D. This is going to be equal to my deflection here, my delta KL. Negative PKL cubed over 3EI. Sorry, I didn't realize how quickly I brushed that aside, but if you need more time to write that down, here it is. My delta of x equals Cx plus D, 0 to 1 minus KL. This is going to be equal to negative P KL. Let me make sure that I do this properly. KL squared over 2EI minus what is it? (3EI). And when I plug in these values, I end up getting, I can rewrite this as L minus KL. I believe, yes. When I plug that in, I end up getting sorry, this is squared. No, I'm sorry, I messed this up somehow. What did I do? I have PKL squared over 2EI. This should be it's okay. Keep calm and carry on for now, right? This is minus P. So what I did here was this one should be times squared times L. And I believe that should give me PKL cubed over 6EI. For 2EI. And that is my delta at KL. Sorry, this is my delta at C. So as you can see, this was actually a pretty long process going all the way through, but it was an interesting process. This is about as complicated as you should expect on the quiz. But let's see what happens if you try using a different method. If I try using moment area, I might be able to get the solution much faster. Well, not much faster, but with less work. So this is using moment area. This is also using, this is moment area slash, oh yeah, this is moment area. So TCA equals, sorry, what am I doing? If I want to find the deflection at the end, I just need to find a Q diagram, which has oh, sorry, I don't even need my Q diagram. I just need my diagram. This is PKL. This is KL. Do you guys agree that if I draw my deflected shape, it ends up looking something like this? This distance here is TCA. That just happens to equal delta C because we're working with a cantilever. And all I need to do now is say, well, what is TCA? TCA is equal to the moment of my M over EI diagram from A to C times centroid at A, or centroid at C. Notice that these two letters are always going to be the same. And what is that? What is my centroid? Well, what is my area? My area, sorry, my moment is the area times the centroid. So what is the area? The area is PKL times KL times 1/2. What is the centroid? The centroid from C is the distance from here to here. And that distance is the same as, do you read that this distance is the same as L minus this distance? So this distance here is the same as L minus KL on 3. And if I work this out, I should end up getting now you'll notice that these two have different signs. I have P over 6 minus P over 2 up here. I have P over 2 minus P over 6 here. That is because this one is based on downward being positive. Well, it's not based on downward being positive. This is based on your tangent. It's based on knowing what the deflected shape should be. This one is, the differential equation method normally assumes that your deflection is pointed upwards. So is there something that you should keep in mind as you're working on these things? That always keep in mind what the deflection should be when you're trying to keep track of your signs. If I want to find delta, or if I want to find theta at C, I can just use delta C, delta theta. Recall that delta theta is equal to delta C minus, equals theta C minus theta A. Well, my theta A is just 0 because I have a hinge, so my delta theta is equal to my theta C. And that is just equal to the area underneath my moment diagram, which we already found. And this is the same thing, just opposite signs of what we got over here. Okay, so yeah, that's pretty much everything I wanted to show here. I'm going to include one more video a little bit later. That's basically going step by step through problem 3 of tutorial 7, which is the homework you just turned in. And I believe by going through it step by step, you should actually be able to understand the virtual work method. This is moment area, differential equation method already, and we'll do virtual work with that problem because that was a pretty interesting problem. It's, yeah, well, and I need to let my battery recharge for a while. So, yes, we'll work on that in a few minutes.